Hello everyone, welcome to In 5 Minutes. In this video we are going to see the next problem on higher order differential equation type 2. So this is our question and this equation is of the form f of d into y equal to x, where x is cos x and f of d is this term. So the solution for this equation is given by y equal to yc plus yp, and first we will concentrate on yc. So yc we consider an auxiliary equation, and auxiliary equation is nothing but f of d equal to 0. So we are going to substitute this f of d equal to 0. So this part is equal to 0. The highest power of d is 5. So this equation will have 5 roots. So how to find these 5 roots? So if you consider here it is d minus 1. So we are going to pair these 3 brackets. So from these two I can take d raised to 4 common and I will get d minus 1. Similarly, from this 2 I can take 2d square common, I will get d minus 1 plus d minus 1. Now from these 3 terms I can take d minus 1 common and I will get d raised to 4 plus here it is 2d square, and here we have taken d minus 1 common, so we are remained only with 1 equal to 0. So if you observe, this part is nothing but d square plus 1 the whole square. You can expand this, then you will get this term only, and d minus 1 equal to 0. So our one root is d equal to 1 and another root will be d square plus 1 the whole square equal to 0. So which is d square plus 1 into d square plus 1 is the repeated roots. And when we get d equal to plus minus I, because it is a plus 1, it will become d square equal to minus 1, and we cannot take the root of minus, so it will becomes imaginary. So we get two equation, d equal to plus minus I. One is for this d square plus 1 and another is for this one. So we have d equal to plus minus I and d equal to plus minus I. So if you see, we have total 5 roots. One root is d equal to 1, two roots are plus and minus I, and other two roots are plus and minus I. So these are the roots. So our complementary equation is given by c1 e raised to m1. In our case m1 is 1, so x plus, if you see, we have complex roots also, and complex roots are repeated. So for repeated roots, we used to have c2 plus c3x, but this is a complex root, so we have alpha plus minus I beta. In our case, alpha is 0 and beta is 1. So e raised to 0x into the constant, here we have written c2 plus c3x because the roots are repeated, into cos of beta x, beta is 1, x, plus again the constant. In constant we will write c4 plus c5x because the roots are repeated twice. Therefore we have two constants and one constant will be multiplied by x into sin x. So this is our complementary part. Now we will find yp. So yp is 1 upon fd into x. What is fd? fd we have just calculated as d minus 1 into d square plus 1 the whole square, and x is nothing but cos x. So if you can see, we have d square term here, but we do not have here. So keep this part as it is, d square plus 1 the whole square. For this part we will multiply and divide by d plus 1. We take the conjugate of this and we multiply and divide. So the conjugate of this part, here it is d minus 1, so it will become d plus 1. So in the numerator we will have d plus 1 into cos x, and in the denominator d minus 1 and d plus 1 is nothing but a minus b into a plus b. So it will be a square minus b square, so it will become d square minus 1.